I'm glad to see all of you here today. And today I will present a summary of my thesis, which is titled Characterization and Utilization of Interactions in Wet and Dry Cellulose Nanofibrillar Networks. And I will jump right into the outline. So I will start by giving a brief background on wood-derived cellulose fibers and fibrils and their interactions in the presence of liquid water and upon water removal. And then I will state the objectives of this thesis. I will then move on to present the materials that have been used in this thesis. And then I will present the results and discussion, which I have divided into 3 sections. And in the first section, it is called Minimizing the Water Uptake in Fibrillar Networks by Drying-Induced Interactions. In part 2, Maximizing the Water Uptake in Fibrillar Networks, an experimental and theoretical description. And part 3 is Potential Applications, where we develop fibrillar hydrogel actuators and superabsorbent structures. And then I will finalize with the conclusion. So the presence of water in cellulose-based materials is often seen as a detriment. Everyone knows what happens to corrugated paper in very humid conditions or to paper immersed in water. It loses its mechanical strength and can even disintegrate. However, the affinity to water is also a necessity for fiber swelling and fiber flexibilization, which is a prerequisite to create strong fiber-fiber joints in paper making. And it is also useful for the liquid absorption in hygiene products, and it is naturally necessary for the water uptake in plants. And all of this is to say that the cellulose-water relationship is paramount in the handling of fibers and fibrils, and there is a need to be able to predict or know how to reduce or enhance the water uptake. But forming this understanding is not trivial with fibers, because they have a complex composition and structure over different hierarchical length scales. And the basic reinforcing element of wood is the aggregates of cellulose nanofibrils, termed fibril aggregates. And these are embedded in a matrix of hemicellulose and lignin. And the cellulose nanofibril is composed of linear chains of the cellulose polymer. And due to this ordered interior of the CNFs, they have a very high elastic modulus. So CNFs are particles with a high aspect ratio. They have a defined geometry and chemical composition and a high specific surface area. And in this work, we've focused on using mainly chemically modified nanocellulose. And a particular challenge in fiber and cellulose-water interactions are the drastic and more often negative changes that occur upon drying of cellulose-based materials. And these property changes are known as hornification, and they're generally viewed to be irreversible or at least very stable. And hornification encompasses a bunch of property changes, such as increased fiber stiffness, reduced fiber flexibility, aggregation at different structural levels of the fiber wall, and perhaps most notably, a reduced ability to hold water. And it is also associated with cost issues in industry. And what's interesting, however, is that drying results in a similar reduced ability to hold water at different length scales of cellulose. It occurs with macroscopic fibers, it occurs with cellulose nanofibrils, and it even occurs with dissolved and regenerated cellulose polymers. So in this thesis, the objectives has been to utilize cellulose nanofibrils as model materials to investigate and describe the interactions that govern changes in the swelling behavior of the cellulosic networks. And herein, we've established factors that govern the swelling with the focus on drying-induced interaction. We've established models to describe the fibrillar network structure, and then this knowledge has been utilized to control the water uptake in fibrillar networks for potential applications. And related to this thesis are the UN Sustainability Goals number 9 and number 12. So the nanofibrils were prepared by chemically modifying different pulp fibers. Here we've used different sulfide pulps with different hemicellulose contents, as well as hemicellulose-rich fibers, which I will refer to as holofibers or holo-CNFs. And the modified fibers were then mechanically disintegrated to obtain a transparent CNF gel. And the CNF gel was then further diluted to obtain colloidally stable CNF dispersions. And the resulting fibrils had widths of around 2 to 4 nanometers and were over 500 nanometers in length. And here we chose to work with anionically charged carboxylated fibrils by tempo oxidation and carboxymethylation, and cationically charged fibrils by quaternization. And from this, we can form different fibrillar networks. So by reducing the double layer repulsion between the fibrils by the addition of acid, for example, we can form attractive colloidal gels, and these have an isotropic structure. Or by increasing the CNF concentration by filtration, we can form repulsive colloidal glasses, and these have an anisotropic structure. So I will start by discussing part one, where we look at the interactions that lead to minimizing the water uptake in fibrillar networks. And in this first project, we prepared carboxymethylated and hollow CNF sheets by vacuum filtration and hot pressing for sheet formation. And the carboxymethylated sheets were then immersed in different metal salt solutions for counter-ion exchange. And the resulting swelling of these sheets differed then because of the presence of the different counter-ions. And these sheets were then exposed to a heat treatment to induce hornification. And the heat treatments were performed at temperatures between 105 and 150 degrees for different durations. And the sheets were subsequently immersed in water and allowed to swell until equilibrium. And then we defined a relative reswelling degree, which is the reswelling of the heat-treated sheets with respect to a non-treated sheet. And I will also refer to this as their aging reswelling behavior. So if we look at the sheet in the sodium form that was carboxymethylated, we found a clear correlation between the heating time and temperature to the reswelling, such that longer heating times and more elevated temperature reduced the reswelling and therefore intensified the hornification. And this was also the case with lithium and cesium as counter-ions, which indicates that the specific ion effects or hydration energies of these cations do not significantly affect the hornification process. However, with protonated carboxymethylated sheets, we did not obtain a similar heating time or temperature dependence. However, with these sheets, they generally exhibited low reswelling degrees due to the neutralization of charged groups in the network. If we instead introduce a divalent counter-ion or use hollow CNFs, we obtain a less prominent and more linear relationship to the reswelling degree. And this indicates that hornification is hindered to some extent. And in the case of magnesium, this could be related to the larger hydration of the ion, which could affect the kinetics of water removal. And with hollow CNFs, this is likely related to the partial hemicellulose coverage on the fibrils, which would obstruct close fibril-fibril contact. However, we found the heating time dependence of the monovalent counterions of particular interest. So we explained this relationship by introducing an empirical exponential expression to describe Fickian diffusion. And the diffusion exponent indicates a Fickian diffusion for n equals to 0.5. However, since we're investigating the effect of the heating time on the reswelling degree, we should obtain an inverse relation. So by plotting the reswelling as a function of 1 over the square root of time, we obtain a nearly linear relationship. And this indicates a hornification process based on molecular diffusion. We then further continued to look at the long-term swelling of the aged sheets. And what we noted was that equilibrium is not actually reached after 24 hours. Rather, the sheets continue to reswell, but this is on a much slower time scale. And this continued for at least up to a year. And interestingly, the hollow CNFs exhibited the highest increase in reswelling. And this could be related to the limitations in dense packing due to the branched and non-ordered structure of the hemicellulose. We further characterized the aged CNF sheets, and we used solid-state NMR to evaluate the supramolecular structure at various degrees of heat treatment, and wax to evaluate the crystalline ordering of the fibrils. And here we did not find an increase or change in the degree of crystallinity, which is related to the ratio between the signals assigned to the surfaces and interiors of crystalline domains. However, by spectral fitting, we obtained an increase in the fibrillar aggregate dimensions as a result of the heat treatment, and this was significant with sodium as a counterion. We then employed a multivariate FTIR analysis with the help of Mats Josefsson and Olof Svensson at AstraZeneca, and this was to evaluate the formation of covalent bonds as a consequence of the heat treatments. And in short, the process is based on projecting the spectral data onto a coordinate system of reduced dimensionality, which is then described by certain latent variables. And these variables describe the most extensive variation between the samples. And this is here visualized in a score plot. So in the score plot, what we did obtain was that the non-treated sheets and the sheets treated at the highest temperature were quite distinct, and we also saw a clustering of each temperature. And one of the main findings, however, from this was that we obtained unique spectral variations for the sheets heat treated at 150 degrees. And this was especially an increase in the signal intensity assigned to the carbonyl group, which could indicate hemiacetal or ester crosslinks. However, hornification occurs at lower temperatures, so we concluded that this cannot be the main cause of hornification. The macroscopic properties of the CNF sheets are affected by the heat treatment, so we evaluated their tensile properties to obtain insights on the effect of hornification on the fibrillar network structure. And one of the clear trends we obtained was an increase in the wet stiffness and wet strength with increasing heating times. And this was especially notable for the protonated sheets. And so to further evaluate this, we performed a counterion exchange on the sheets that were aged in the protonated form and converted back to sodium form via a bicarbonate buffer. And when we did this, what we obtained was a similar reduced swelling and tensile properties as if the sheets had been aged in the sodium form. And this indicates that the properties of the fibril joints, which are formed upon hornification, remain the same regardless of the two counterion forms. And it also indicates that the regions that were exposed to deprotonation are still accessible for counterion exchange despite the hornifications, which would mean that these regions do not hornify. And now that we have gained some insights into the interactions that minimize the water uptake in fibrillar networks, we investigated some of the factors that maximize the water uptake in fibrillar networks. And in this work, we prepared CNFs with different aspect ratios that were either tempo-oxidized or carboxymethylated to charges between 0.5 to 0.7 millimoles per gram. And this was done by starting with fibers with different initial hemicellulose content, such that higher initial hemicellulose content resulted in longer fibrils, indicating a better preserved fibril structure. And from this, we prepared isotropic and anisotropic hydrogels and evaluated their mechanical properties. So we evaluated the rheological properties of isotropic hydrogels, which were locked by acid. And from the storage and loss modulus, we obtained that the stiffest hydrogels were formed by the high aspect ratio fibrils. However, the holo CNFs have an even higher aspect ratio, but their lower stiffness was attributed to a lubricating effect from the remaining hemicellulose on the fibrils. And in the creep experiments, different shear stresses were applied and the resulting strain was measured. And here, the high aspect ratio CNFs showed the highest ability to recover, but interestingly, all the carboxymethylated fibrils were able to endure one more stress relaxation cycle before complete yielding. And this trend shows that the carboxymethylated fibrils seem to form stronger interacting networks. We then evaluated the tensile properties of anisotropic hydrogels that were locked with calcium as counterion. And here, we obtained similar tensile properties of both chemical functionalities. Rather, the deformation behavior was more dependent on the aspect ratio. So shorter fibrils, that is the low aspect ratio fibrils, formed the stiffest and the stiffest sheets with the highest wet strength. And this was then, it was found to be related to the different water contents of the sheets. So the shorter fibrils can pack more densely during sheet formation, which results in a lower reswelling degree. However, longer fibrils would require to bend around each other in the dried state to fill all pores, and this can create a network with more dried-in stresses or hidden lengths, which then can swell up more in the presence of water. So because of this, we found that the wet modulus was proportional to the volume fraction. So we integrated this data, as well as for sheets that we treated with other metal ions, into a beam bending model. And from this beam bending model, we found a nonlinear relationship between the wet modulus and the volume fraction. And this has been shown previously. And this indicates or shows that there are separate contributions to the wet modulus from the aspect ratio and from the choice of counter ion. So by looking at the network topology as a function of the aspect ratio, we could elucidate this effect, and we found a linear relationship, which indicates that the aspect ratio does affect the network topology. And here, the different counterions end up with approximately similar values, and this indicates that the counterion species does not significantly affect the strength of the fibril contact point. Rather, the ion species affects the wet modulus indirectly via the equilibrium solidity. So now that we have looked at factors that lead to a reduced or enhanced water uptake, we will look at some potential applications of these fibrillar networks where the water uptake is important. So the possibility of creating highly anisotropic fibrillar structures that are physically cross-linked in one plane also means that the swelling is highly directional and can be maintained by the structure under load. As an example, a CNF sheet can swell up to 30,000% in the out-of-plane direction while only maintaining a 20% swelling in the in-plane direction. And this is an advantage in creating, for example, hydrogel-based actuators suitable as perhaps artificial muscles of soft robots designed for delicate tasks, or for super absorbent structures, which can replace fossil-based super absorbent polymers used in hygiene products today. And this is what I will discuss in the last part. So we wanted to explore the actuation performance of CNF sheets by optimizing the fibril network relationship. And as the sheets are allowed to swell under constraint in such a parallel plate setup, they generate a force. And with respect to the area size of the sheets, this is the blocking pressure. So the blocking pressure is the pressure required to almost fully prevent swelling, and this is related to the osmotic swelling. And the buildup of osmotic pressure can be described by several terms. So it's related to the liquid polymer mixing, it's related to the difference in ion concentration inside and outside the network, and it's also related to the mechanical restraining forces of the network. So by altering the surface charge, the functionality or the aspect ratio of the fibrils, as well as the drying process of the sheets, we can form fibrillar hydrogels with different actuation capacities, rates, and achievable strains. So we looked at their blocking pressure development, and some of the main findings we had were that increasing the surface charge increases the blocking pressure, but it also increases the rate of pressure generation. And a similar effect is found with increasing the aspect ratio, although less prominent. We found that a sufficient drying is important for the in-plane reinforcement because the in-plane stiffness is needed to direct the swelling pressure. And then we found a nonlinear relationship between the actuation area and the blocking pressure, such that decreasing the area increases the blocking pressure. So from this, we determined the actuation rates and the time to reach 90% of the maximum pressure. And what we found was by using highly charged fibrils with very small actuation areas, we can reach up to 5 megapascal in less than a minute. And as a comparison, hydrogel-based turgor actuators, which are some of the best performing actuators today, takes several hours to reach around 1 megapascal. We then looked at the displacement of these hydrogels because this is an important parameter in the design of actuators, and I will refer to this as their strain. And this was done by a stepwise expansion in the same parallel plate setup. So one of the main findings here was that by using highly charged fibrils, we can reach strains of up to 3,200%, which far surpasses conventional polymer hydrogels. However, by decreasing the area size, which was found to increase the blocking pressure, we noted that we lose in the maximum strain attainable. And this is suggested to be related to a decreased in-plane stiffness with the decreasing area sizes, and it is also supported by the increased in-plane swelling ratio of smaller areal sizes. Although much more work needs to be done for complete actuation control of these fibrillar hydrogels, already at this infant stage, they show large potential due to their high actuation pressures and fast response times, which is due to the anisotropy and the nanoporous network. We determined the maximum work density reached in this work, which was around 4,000 kilojoules per cubic meter. And to put this into perspective, this is 100 times higher work density than biological muscle. So this was one example of how we can use this anisotropy to make actuators, but these systems can also be used in modern hygiene products, which brings us to the last project. So in the final project, we prepared a superabsorbent heterostructure, and this really just means that we used two separate cellulose-based structures and combined them to form our superabsorbent. And as the storage component here, we used cationic holo-CNF sheets, and we chose cationically charged because they demonstrate higher swelling than anionic charges at equivalent charges. And then we started with hemicellulose-rich fibers because we knew that we could preserve the fibril structure and form longer fibrils that can then contain higher equilibrium swellings. So here we had an aspect ratio of around 1,000. And due to the preparation method, we could form sheets with or without fiber fragments. We then looked at the water uptake of the CNF sheets, both in regular water and in a physiological saline solution. And here we found that the completely fibrillated networks reached slightly higher water uptakes, and this could be related to the somewhat higher nano yield and surface charge in these sheets. However, with increasing ionic strength, we had a notable reduction in the water uptake ability for both sheets. And this notable reduction is related to the diminished difference in osmotic pressure across the CNF gel boundary. And this is also the case for other conventional superabsorbent polymers, such as polyacrylates, which are the most highly charged polyelectrolytes. To further evaluate the liquid holding capacity of these CNF sheets, we measured their swelling pressure at different water uptakes. And here we found that the sheets with the fiber fragments, that is the coarse CNF sheets, could maintain a swelling pressure at the highest water uptake. And this could be related to an increased in-plane stiffness or in-plane reinforcement caused by the presence of these fiber fragments, which has shown to be important in the actuator data. So we decided to continue with the coarse CNF sheets in the continuation. So the heterostructure also consisted of a fiber-based aerogel, which is responsible for the rapid absorption and spreading of liquid to the CNF sheet. And so to evaluate the ability of the CNF sheets to drain the aerogels, we performed automatic pore volume distribution measurements on the aerogels to evaluate its pore size distribution, as well as the extent to which water can be retained within the structure under increasing air pressures. And we then combined this data with the swelling pressure data of the CNF sheets. And from this, we found that both in water and in a physiological saline solution, the swelling pressure reached by the CNF sheet is high enough to drain the aerogels. And even at a 98% saturation of the CNF sheets, they still reach above the critical pressure needed to drain the aerogel. We then integrated the CNF sheets into the heterostructure and measured the water uptake in the whole structure. And this was done by lowering the sample into a water reservoir. And we did this with a water reservoir with a volume of water above the saturation capacity of the aerogels. And from this, we found that the liquid uptake divided into two regions. The first region reflects a rapid absorption, which is related to the instant saturation of the aerogel. And the second region, with a much slower rate, is attributed to the transfer of liquid from the aerogel to the CNF sheets. And in a saline solution, the second region reaches almost instant saturation, as found previously for only the CNF sheets. We then performed a similar measurement. However, this was done in a limited water reservoir, which is a volume of water below the saturation capacity of the aerogels. And we then measured the liquid uptake in only the CNF sheets. And here we found that the liquid uptake in the CNF sheets was quite a bit lower. However, it still demonstrated a rather efficient transfer of liquid from the aerogels to the CNF sheets. So this was another demonstration of how we can then utilize the liquid uptake in fibrillar structures to design modern hygiene products. And this takes me to the conclusion. So in this work, we used anisotropic fibrillar networks as model systems for fundamental studies. Their uniaxial swelling allows for a large dynamic range in which cellulose-cellulose and cellulose-water interactions can be studied. And we showed that the route to hornification matters, which is emphasized by a clear heating time and temperature dependence. We then established a mechanical network model to elucidate the influence of aspect ratio on network topology. And then we utilized the water uptake in these fibrillar networks to develop tunable actuators, and we demonstrated a method for the preparation of an all-cellulose superabsorbent which can retain liquid under load. So I would like to acknowledge my supervisors, Professor Lars Wågberg, Professor Thomas Larsson, and Dr. Tobias Benselfelt. I would also like to thank Knut and Alice Wallenberg Foundation through the Wallenberg Wood Science Center for funding my PhD. And then I would like to thank my friends and colleagues at the Department of Fiber and Polymer Technology, as well as my co-authors. And thank you all for listening.